Now, let's continue. The forces acting on the body act as vectors, and so the total force on the body depends upon both the magnitudes and the directions of the individual forces. When the net force on the body is equal to zero, then by Newton's second law, the body does not accelerate, and it is said to be in mechanical equilibrium. A state of mechanical equilibrium is stable if, when the position of the body is changed slightly, the body remains near that equilibrium. Otherwise, the equilibrium is unstable. A common visual representation of forces acting in concert is the free body diagram, which schematically portrays a body of interest and the forces applied to it by outside influences. For example, a free body diagram of a block sitting upon an inclined plane can illustrate the combination of a gravitational force, normal force, friction, and string tension. Newton's second law is sometimes presented as a definition of force, or maybe a force is that which exists when an inertial observer sees a body accelerating. In order for this to be more than tautology, acceleration implies force. Force implies acceleration. Some other statement about force must also be made. For example, an equation detailing the force might be specified, like Newton's law or of universal gravitation, by inserting such an expression for F into Newton's second law. An equation which predictive power can be written. Newton's second law has also been regarded as setting out the research programs for physics, establishing that important goals for the subject are to identify the forces present in nature and to catalog the constituents of matter. Newton's third law. Overly brief paraphrases of the third law, like action equals reaction, might have caused confusion among generations of students. The action and reaction apply to different bodies. For example, consider a book at rest on the table. Earth's gravity pulls down upon the book. The reaction to that action is not a support force from the table holding up the book, but the gravitational pull of the book acting on the earth. So here's the presentation of this picture, which is a man stepping out of the boat. Newton's third law relates to a more fundamental principle, the conservation of momentum. The latter remains true even in cases where Newton's statement does not. For instance, when force fields as well as material bodies carry momentum, and when momentum is defined properly in quantum mechanics as well. By Newton's second law, the first term is the total force upon the first body, and the second term is the total force upon the second body. If the two bodies are isolated from outside influences, the only force upon the first body can be that from the second and vice versa. By Newton's third law, these forces have equal magnitude but opposite direction, so they cancel when added and P is constant. Alternatively, if P is known to be constant, it follows that the forces have equal magnitude in opposite direction. Candidates for additional laws. Various sources have proposed elevating other ideas used in classical mechanics to the status of Newton's laws. For example, in Newtonian mechanics, the total mass of a body made by bringing together two smaller bodies is the sum of their individual masses. Frank Wilczek has suggested calling attention to this assumption by designating it Newton's zeroth law. Now, the candidate for a zeroth law is the fact that at any instant, a body reaction to the forces applied to it at that instant. Likewise, the idea that forces add, like vectors, or in other words, obey the superposition principle, and the idea that forces change the energy of a body have both been described as a fourth law. Moreover, some texts organize the basic ideas of Newton mechanics into different postulates, other than the three laws as commonly phrased, with the goal of being more clear about what is empirically observed and what is true by definition. Examples: the study of the behavior of massive bodies using Newton's laws is known as Newtonian mechanics. Some example problems in Newtonian mechanics are particularly noteworthy for conceptual or historical reasons. Uniformly accelerated motion. If a body falls from rest near the surface of the earth, then, in the absence of air resistance, it will accelerate at a constant rate. This is known as free fall. The speed attained during free fall is proportional to the elapsed time, and the distance traveled is proportional to the square of the elapsed time. Importantly, the acceleration is the same for all bodies independently of their mass. This follows from combining Newton's second law of motion with his law of universal gravitation. The latter states that the magnitude of the gravitational force from the earth upon the body is F equals gm, the mass, over r squared, where m is the mass of the falling body, m is the mass of the earth, g is Newton's constant, and r is the distance from the center of the earth to the body's location, which is very near the radius of the earth. So here's the picture of this. Setting this equal to ma, the body's mass m cancels from both sides of the equation, leaving an acceleration that depends upon g, m, and r can taken to be constant. This particular value of acceleration is typically denoted g equals gm over r equals 9.8 m over s squared. If the body is not released from rest but instead launched upwards and or horizontally with non-zero velocity, then free fall becomes projectile motion. When air resistance can be neglected, projectiles follow parabola-shaped trajectories because gravity affects the body's vertical motion and not its horizontal. At the peak of the projectile's trajectory, its vertical velocity is zero, but its acceleration is g downwards, as it is at all times. Setting the wrong vector equal to zero is a common confusion among physical students. So this could maybe a progress. This is part 2, because I'm making more presentations about this topic. So see you for part 2. Sorry, this is part 3. Wait. See you in part 3.